Hello and welcome to today's lesson looking at the acceleration required practical in the forces topic of GCSE Combined Science Physics. So in today's lesson we're going to look at the force and acceleration required practical and look to apply Newton's laws of motion to the real world. So in today's lesson, if we are successful and we learn, we can understand how the acceleration of an object depends on the size of resultant force acting upon it. We can understand how the acceleration of an object depends on the object's inertial mass acting upon it, and we can review how to collect and analyse experimental data based on the scientific method, which falls into the following part of the AQA Combined Science specification for physics, and we're looking in particular at Required Practical 19, which falls into the forces topic on paper 2. So, there are laws of motion that determine the movement of all objects in the universe. So law 1, the law of inertia. All objects will travel at the same velocity, so the same speed, in the same direction, unless it is acted upon by a resultant force. So a resultant force causes acceleration. Now, inertia is the tendency of objects to continue in their state of rest or of uniform motion when there's no resultant force acting upon it. So if an object is moving in a particular direction, it will continue to move at the same speed in the same direction if no resultant force acts upon it. That is inertia. So that's a very important idea, that objects wish to remain at the same velocity unless a resultant force acts upon them. Now, a resultant force is an overall force on the object. The resultant force is the combination of the different forces on an object. Now, you can calculate the resultant force by finding the difference between the forces in the same plane. So in this example, we have 20 up, 10 down, so do 20 minus 10 equals 10 newtons upwards. Now we do this because we consider one force a negative because it's acting in the opposite direction. Now in a free body diagram, such as the one shown on this slide, the length of the arrows in the free body diagram help you understand the values of the forces. Now the resultant force can replace all the other forces in the diagram, so when a number of forces acting on an object can be replaced by the single force that has the same effect as all of the original forces acting together, that is the resultant force on an object. Now, resultant forces can replace the forces in the diagram, and objects will always accelerate in the same direction as the resultant force. So the size of the acceleration is affected by the mass of the object, which is the second law of Newton's laws of motion. Law 2, F equals ma, that the resultant force in newtons is equal to the inertial mass in kilograms times by the acceleration in meters per second squared. So it tells us that this is the mathematical interpretation of Newton's first law, that the acceleration experienced by an object is dependent on both the inertial mass of the object and the resultant force acting on the object. So you've got those two factors affecting acceleration. Now, acceleration is directly proportional to the resultant force acting on the object. So in theory, if you plotted resultant force against acceleration, you would get a straight line through the origin, because a graph which has a straight line through the origin, indicates direct proportionality. But acceleration is inversely proportional to the mass of the object. But the full name for mass in this context is actually the inertial mass. Now, the inertial mass is a measure of how difficult it is to change the velocity of an object. The larger the inertial mass, the harder it is for the object to change velocity. So the larger the inertial mass, the harder it is for an object to accelerate. Because, inertial mass is equal to resultant force over acceleration. We've rearranged the equation above to make inertial mass the subject, the term by itself. So this means that we can actually define inertial mass as the ratio of resultant force over the acceleration experienced by the object. So the larger the inertial mass, the greater the resultant force needed for the same acceleration. But the smaller the inertial mass, the lower resultant force needed for the same acceleration. So the larger the inertial mass, the greater the inertia of the object. Now, this equation is something you've got to memorize for your examination, because it's a very common equation used in examinations. Whilst the third law is that when two bodies interact, they exert equal but opposite forces on each other of the same type. Now, this gives each object in the system a resultant force, so it makes both objects accelerate. So for this law to work, you've got to have two objects in your system. So, for example, a person and the ground. Okay, now the forces are produced in equal size and are the same type, but they are acting on two different objects and they act in opposite directions. So this law produces the same resultant force on two different objects. Now this can produce different accelerations on the two objects if they have different masses, because it's both the resultant force and the inertial mass that affects your acceleration. So let's just revise what we've learned so far. First law of motion. All objects travel at the same velocity unless they're acted upon by a resultant force. A resultant force causes acceleration. Law 2. The resultant force in newtons equals the inertial mass in kilograms times by the acceleration in meters per second squared. And law 3. When two bodies interact, they exert equal but opposite forces on each other of the same type. Now just remember again, inertia is the principle that a moving object has a tendency to stay at the same velocity as long as there is no resultant force acting upon that object. Now, what we're going to do is we're going to try and find the relationship experimentally between the resultant force and acceleration for a moving object. So if you can find the relationship between the resultant force of a moving object and its acceleration, you've achieved the aim of this required practical. So what do you need? You will need a trolley, a meter ruler, a pencil, chalk, masking tape to mark the intervals, a bench pulley, string, a small weight stack, a stopwatch and a blue tack. So what will you do? You'll use the ruler to measure intervals on the bench and draw straight lines or place tape across the bench at these intervals. Attach the bench pulley to the end of the bench. Tie a length of string to the trolley. Pass the string over the pulley and attach the weight stack to the other end of the string. Make sure the string is horizontal and is in line with the trolley. Hold the trolley at the start point, attach the full weight stack, 1 Newton, to the end of the string. Release the toy car or the trolley at the same time as you start the stopwatch. Press the stopwatch in the lap mode at each measured interval on the bench, and for the final time at 100 centimeters, record the results table. Repeat steps 5 to 8 for decrease in weights on the stack. So 0.8, 0.6, 0.4, 0.2 newtons. Use that to work out the average acceleration of the journey, and you can plot force against acceleration and see the relationship. Now that's one methodology of using equipment such as this, as shown on the diagram. However, there's another way to do this experiment, and I'll talk you through it now. So, like previously, place a trolley of known mass on a bench attached to a set of known masses with a string and pulley. Now this experiment, the point like I mentioned before, is to verify F equals ma, the second law of Newton's laws of motion. So the known masses, will provide a resultant force downwards, the weight, which we can calculate with the equation weight equals mass times by gravity. Now, when measuring the known mass attached to the pulley, we've got to consider the mass of the hook and the mass of the masses together. Now, this will produce a resultant force downwards, and this will accelerate the trolley of known mass. So it will cause a resultant force downwards and cause the trolley to accelerate along the bench. So you'll get that acceleration of the trolley. Now, changing the known mass attached to the string will change the resultant force experienced by the trolley, and then that will obviously affect or may not affect the acceleration depending on what you think will happen in this investigation. So when the known mass is released, this will cause the trolley to accelerate along the bench. Now, as the trolley moves, the trolley will experience friction. This will dissipate some of the energy to the internal energy of the surroundings. So that is not wanted, and that will give us inaccurate results in our investigation. So to remove friction, you could carry out the experiment on an air track, as the trolley would not be touching the bench, and so that will remove friction because friction is a contact force. So carrying it out where there was no contact, where the friction is removed, that will make the results more accurate. Now, what you then need to do is then measure the acceleration of the trolley as it moves along the bench. So what we do is we place a light gate connected to a data logger over the trolley and place a card on the trolley. Now the light gate is connected to a data logger which can calculate the velocity of the trolley. Now as the trolley moves along the bench, the front of the card passes through the light gate. This allows the data logger to record velocity 1, the first velocity. Then as the trolley keeps on moving, the back of the card passes through the light gate, and this allows the data logger to record velocity 2. Now this will allow your data logger to work out the acceleration experienced by the trolley, because we know change in velocity will be velocity 2 minus velocity 1. Then acceleration is then going to be the change in velocity over the time taken to move between the front part of the card hitting the light gate and the back part of the card hitting the light gate. Now, for this to gain accurate results, the string must not be slack, otherwise some of the resultant force will be used to tighten the string. So you've got to make sure the string is completely tight before you start the experiment. And then also the known masses, the weights in this example, must not hit the ground before the back of the card passes through the light gate, as it is the masses fallen which produces the resultant force. So if the masses hit the ground before the second measurement is taken, that will give us inaccurate results because it would stop the trolley accelerating. Now, the fallen masses should produce a constant resultant force, as the strength of gravity on Earth never changes. So the weight of these known masses should stay the same. So therefore, this resultant force, which accelerates the trolley, is constant throughout this investigation. Now, what we'll do is we'll carry out this investigation. We'll measure the acceleration for that particular mass, and then we'll change the masses. So we can do 20 grams, 40 grams, 60 grams, 80 grams, and 100 grams to produce the weight and resultant force. So this gives us resultant forces of 0.2 newtons, 0.4 newtons, 0.6 newtons, 0.8 newtons, and 1.0 newtons used to accelerate the trolley. Now, however, when we're doing this, the weight is accelerating both the trolley and the known masses, because the known masses are falling to the ground and accelerating downwards, as well as the trolley accelerating along the bench. Now, for this practical to work, the mass must remain constant, because we're trying to prove F equals ma, and we're trying to see how A and F relate to each other. So for this to be a fair test, for the results to be accurate, you've got to have a constant value for m. So m can't change in this practical. Now, this means the overall mass of the system needs to stay constant. So when masses are added to the known mass to accelerate, they must be taken from the mass of the trolley to keep the overall mass of the system the same. So for example, if you wanted to add 20 grams to your value of known masses, which are being used to accelerate the trolley, those 20 grams have to come from the trolley itself, because that then allows the mass of the total system to remain constant and makes mass a control variable, which is what it should be if you want to get valid data in this experiment. Now, so as I said before, this keeps the mass of the overall system the same. Now, once you've done that, you should plot the average acceleration on the x-axis and the force attached on the string on the y-axis, and draw a line of best fit on your graph. Now, in theory, as you're doing this, you should get a straight line through the origin, because the two factors, resultant force and acceleration, are directly proportional to each other. Now, interestingly, you might have thought, why don't we plot average acceleration on the y-axis? Because isn't that the value that you're actually calculating, and that's always what you put on the y-axis. Well, no, in physics, what we do is you put things on the axis in the correct way to allow us to gain values from those particular quantities. Now, if you look on this particular graph, if you have force divided by acceleration, or F over A, you would actually work out m, because if F equals ma, m equals F divided by A. Now, you'll notice the gradient, which is the change in y over the change in x, is going to be force over acceleration. So if you plot it like this, the gradient of this line will give you the inertial mass of the object. Now, what have we learned in this particular lesson? That the resultant force is a single force that has the same effect as all forces acting on the object. If the resultant force on an object is 0, the object stays at rest or at constant velocity. If the resultant force on an object is not 0, the velocity will change. And if two forces acting on an object along the same line, the resultant force is the sum if they act in the same direction, their difference if they act in the opposite direction. Now, if we've been successful and learned in today's lesson, we can understand how acceleration depends on the size of the resultant force acting upon it. In the next lesson, we're going to consider this experiment, but not change force and keep mass constant. We're going to change mass and then keep force constant. And what we should have done in today's lesson is review how to carry out this experiment correctly and how to analyse data based on a scientific method to prove the relationship between acceleration and the size of resultant force acting on the object accelerating. I hope you've enjoyed today's lesson looking at the required practical for acceleration for GCSE Combined Science forces, and I hope you have a lovely day.